So last week we have end up with we talk about how to estimating constraint functions, right? So this constraint function, including function, has to be positive on the whole time interval, or the monotone function, like a monotone increasing or decreasing function, or the function has to be a density function. In that case, the integral of the function has to be equal to 1. So we have talked about the methodology, how to estimating these constraint functions. So today we will go through some R examples and coding how we can doing the estimation based on some real data. Okay, so now I'm give you a demonstration. Okay, so again, we will start with loading the FD library. So first example, we will working on estimating a function with a positive constraint. Okay, so this is the Vancouver precipitation data. So this is the delay precipitation in Vancouver from day 1 to 665. Okay, so for this data, because it's periodic data, so we using Fourier basis function here. So we choose 365 Fourier basis functions, and so in this case, we may have overfitting problem. Therefore, we need to give the roughness penalty to control the smoothness of the fitted function. So so here what we do is we will define this harmonic acceleration differential operator. So this is the form of the harmonic acceleration differential operator. So after we define this harmonic acceleration differential operator, we know that it will not penalize cosine function and sine function, right? Yes. So this is the special things. It will not penalize cosine omega t and sine omega t. So this is and also the linear functions, any linear functions, a plus bt cosine omega t and sine omega t. Okay, so this is a very common differential operator we used to define the roughness penalty when we working on periodic process. So so in this actually in FDA. There's a very easy way to define this linear differential operator. Basically, there's a function called vector to LFD. Okay, so basically, it will treat the linear differential operator in this form. So starting with the highest order of the derivative. So for example, here for this harmonic acceleration differential operator, it starts with the third derivative. Okay, so the third derivative, the high order, always equal to 1, to be equal to 1, the coefficient. Because if it's not equal to 1, you can always divide it by that coefficient to make it equal to 1. So the first one always equal to 1, and then it will define the coefficient to the lower order derivatives. For example, for our case, the coefficient to the second derivative will be equal to 0. The coefficient to the first derivative will be w squared. So w here is 2 pi over the period, right? Yes. So w is equal to 2 pi divided by period of the process. So here the coefficient, this is w2 square, and then the coefficient to f of t, which is you can understand this as a zero derivative of f of t, right? So this coefficient equal to 0. So therefore, you define this 3 coefficient to the lower order derivatives, then you will define this differential operator. So the upper one is always by default is equal to 1, the coefficient. Okay, so after we using this one, so we define this coefficient. Now we will define this linear differential operator. Okay, and also you need to give the range of the time. So here the range of time is from 0 to 365. Okay, so we define this differential operator in this function, and now we will define the roughness penalty. Okay, so the roughness penalty here is defined by this function called FD par. Okay, so you can see here for this roughness penalty, it including the information for the basis function we use. So here we have f basis is basically the 365 Fourier basis function we just defined here, right? And then the Ham LFD, this is to define what kind of differential operator you use to define the roughness penalty. So if you don't have the harmonic accelerating differential operator, you can use other roughness penalty as well. And then you also need to give the value for the lambda. So here we give a pretty large one, is 10 to 7. Okay, so we define this roughness penalty here, and then we will using that function called the smooth dot basis. This is to doing the smoothing splines without any constraints. Okay, so we will do this estimation. So basically, you give the observation for the time point with observations, and then the observed data for these corresponding time points, and then also the roughness penalty. Because in the roughness penalty, this one it contains all basis function and also the roughness penalty term here, right? So we can just using this one. Okay, so we just using this function smooth dot basis function, and this is doing this smoothing splines. Okay, so if we consider these positive constraints, we just using the smooth dot pose as this function. So in this case, it will consider these positive constraints. Okay, still using the same argument as smooth dot basis. Okay, so now we go through this. So as we mentioned that when we do these constraints, the basic idea is to transform the constraints function to the unconstrained function, right? So in that case, there will be no closed formula for the basis coefficients. We have to doing the iterations. So this smooth dot pose is doing this iteration. So here it shows the iteration step, and also the value for the penalized sum square error, and also the gradient length for the iterations. Okay. So then we plotted the fitted curve. So this is the fitted function. Let me see. So PRECFD. So this is without considering the positive constraints. Okay. So we plot the estimated function when we consider the positive constraints. So we were using the function called evaluate dot positive FD. Okay. So we use this function, we evaluate the fitted curve, and then we put this line together. So the black line here is the curve when we have considered these positive constraints. You can see actually it's a very very similar, right? Yes, they are very similar. Okay, so this is to using the same smoothing parameter lambda equal to 10 to 7. So we can also using a smaller smoothing parameter. Here we try lambda equal to 10 to 2. So we can also doing this positive estimation for this consider this positive constraints. So all these functions will be put in GitHub. Okay, so you can download this function in the GitHub. Okay, so this is to use the to make the lambda smaller. Okay, I think here maybe I make a mistake, make some change here. I should try the lambda equal to 10 to 4. Let's run this again and to see what's the difference. Okay, so this is the estimation when we have, so the blue one is to do the estimated curve without considering these positive constraints, lambda equal to 10 to 4, and the black one is when we consider the positive constraints, lambda equal to 10 to 4, and the pink line is when we consider the positive constraints and the lambda equal to 10 to 2. So you can see here, basically this is to give you the ideas. When we using the positive constraints, if we keep the same value of lambda, then the smoothness, this black one and the red one, the black one is much smoother than the blue one, right? So when we consider the positive constraints using a smaller value of lambda, this pink one actually has the same roughness with the blue one when lambda is larger when we don't consider the positive constraints. So in other words, when we consider positive constraints, we implicitly adding the roughness penalty on the estimated functions. Okay, yeah. So this is just give you this message. Okay, so this is the examples when we consider the positive, estimating the positive functions. So now let me give you an example when we estimate a function with the monotone constraints. This example is for the growth data. So here we have let me see how many. So we have 39 boys in the age from 1 to 15, their heights in the age from 1 to 15, to 18, sorry. You can see here, basically this time point is unequal, so it has one measurement every quarter in the age 1, and then after age 1 it will measure every year, and after age 8 it has one measurement every half a year. Okay, so this is the function looks like. So it's unequally measurements. Okay, so this is just want to mention that for functional data we can able to dealing with this unequally spaced observations very easily. There's no special treatment, but for the time series analysis, it requires this observation to be equally spaced. Okay, so this is the benefit when we use functional data. Okay, so now we just get this heights and um, and age. Okay, so now we doing this. First, we will doing set up the using B splines because for the growth curve is not a periodic functions, right? So we were using B splines, and so we keep the order to be 5. The reason is because recall that when we estimate the positive monotone functions, we will estimate the derivative of the function instead, right? So if you look at our slides, so when we estimate these positive functions, we will estimate the derivative of this function instead, right? So in that case, we want to keep this WT to be smooth. In that case, we will using the fifth order for the B splines. Okay, so we add 1. So and also we the age is we will put a 1 knot at each age point. Okay, so we have these basic functions, and we give the range of the age, and now we can define these B-spline basic functions using the create.bspline.basis. And then we can define the roughness penalty. So we were using the second derivative as the roughness penalty. So here we can just define this LFD object equal to 2, means to using the second derivative as the roughness penalty. So you may compare to the function we defined as the harmonic oscillatory differential operator. You have to using this vector to LFD, right? So for if you just using the second derivative, you can just using LFD object equal to 2, means using the second derivative to define roughness penalty. And we're still using the FD par to give all this roughness penalty information, and we define lambda equal to 10 to minus 2. Okay. So this is the defining the basic function information and roughness penalty. And now we will using the smooth dollar basis. This is the function we used before. So this is the estimated function when we don't have the any constraints, right? So this is the estimation. So here we have 39 boys and with 31 observations. So let's plot how the data looks like. So this is the circles. The red circle represented to the observed heights, and the blue one is the observed is the fitted curve, height curve, without consider the monotone constraints. Okay. So so now let's consider the monotone constraints. So you can just using the smooth dot monotone, and then you can do the estimation. So we just focus on the subject 25. So again, when we have these monotone constraints, we're doing this transformation. So there's no closed formula for the basic coefficient. Therefore, we have to do these iterations. Okay, and so we will evaluate the fitted curve using evaluate.monotone FD, and we will fit this curve. And so this is the fit looks like. So for both cases, they are exactly almost looks like goes through all the points, right? All the observations. The reason is because for the heights, it has a very small measurements, right? And therefore it is fine to go through all the points. Actually, if you make it larger, if you zoom in, it will not go through all the points. But because the range is pretty big from the age 1 to age 18, therefore it looks like going through all the points. Okay, but the function is pretty smooth anyway, right? So a way to look at whether the function is smooth or not is we maybe look at the derivative of the function itself. Okay, so here we can look at the derivative of the function. So here, this is the function, this is the derivative estimation when we considering the constraints, which will be the pink curve, okay? And the blue curve is when we don't consider the monotone constraints, okay? So you can see here, the monotone, when we don't consider the monotone constraints, the estimated derivative will be more bumpy, right? Less smooth, okay? So that's the difference. I guess if you tried some other subjects, you may find out if you don't consider the monotone constraints, the estimated derivative may be negative. Means this it will be it's not a monotone function. The phase function is not a monotone. Okay, so that's a benefit when you doing this monotone estimation. Consider the monotone constraints. So your estimated derivative function will be guaranteed to be positive. Okay. So this is the estimation for when they have a monotone constraints. Okay. So any questions? Is this clear? Okay. So now let's look at the examples when we estimating the probability density function. Okay. So here I simulated some data based on standard normal distribution. I have 50 observations, and so this is the histogram of my estimated 50 observations, and then we can set up the basis function for the Wx, the transformed function. Remember, when we estimated the constraint functions, we actually, because xt has these constraints, so we will express xt equal to e to wt over integral of ewt, right? So then this wt will have no constraints, right? So we will estimate wt directly here instead, okay? So we created B-spline basis functions, and we're using order equal to 6, okay? So let's doing the estimation. So I defined the roughness penalty equal to roughness penalty is using the third derivative as the roughness penalty, and also lambda equal to 10 to minus 2. So here, a special thing about this density estimation is that because it's the iteration, right? So you have to give the starting value for the w of t. So here, I treated the wt equal to 0 as the starting value for the wx. Okay, so if I set wxt equal to 0, means all the coefficients to the basis function equal to 0, right? Okay, so this is the starting value for the WFD, and so we will estimate the density function. So we will using the function called density.fd. Okay, so then we can get the density function. After we get the density function, we can get the density, evaluate this density function by this exponential of wt over the constant integral. Okay, so then we can plot the estimated density function with the data. So this is the estimated function, density function, and this is the observed of the data. Okay. Yes. Okay. So any questions for these examples? Is this good? Okay. Okay. So